Hello, everyone. This is the lecture for section 1.1, approximating areas. So hopefully, if you remember from the introductory video, chapter 1 for Calc 2 is going to be, by and large, a very big, very quick sort of review of the very end, maybe the last 1 or 2 weeks of Calc 1. Okay. Um, There is a couple of new things that I'm going to be sort of interjecting here that we're going to see pop up over the course of the semester, and we got to get used to it and just start getting comfortable with it. Okay. But like I said, a lot of this is going to be review. We're going to end chapter 1 with U substitution, if you guys remember what that is. So let's go ahead and get started. The first thing I want to define, this is one of the new things that I need to sort of interject. This is the thing that's going to be popping up over and over and over again over the course of the semester, is this idea of sigma notation. Okay. Suppose we had a sequence of numbers. So suppose we had a collection of numbers, right? Then the summation, if I wanted to grab every single one of those A's, right, A sub n, and add them all together, it would be written out this way, and this is what it would mean, okay? And this is what's usually called sigma or summation notation, okay? Like I said, this is the thing that's going to be popping up over and over and over again over the course of our semester, okay? Uh, One thing I want to get into is, I mean, we can develop this, and we will develop it a lot over the course of this semester, but I'm going to introduce just a couple of properties just for now, okay? Um, let's go ahead and start with this first one. Suppose that I just have a value C. It'd be a random value. It could be 5, it could be 20, okay? And suppose I just want to add it n times, right? This is going to be 20 plus 20 plus 20 plus 20, just n times, right? That's equivalent to just n times whatever that value is, okay? And the way that we sort of explain this is this, right? This left-hand side, right, is C plus C plus C plus C plus dot 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 plus C. And we're doing this, right, n times, right? Excuse me. Since we're doing it n times, right, that just rounds out to that. Simple as that. Okay. And that's the explanation for it. Okay. Let's go ahead and move on to the other one. Suppose we had, right, two sequence of numbers, an AI and a BI, right? And we wanted to add, and both the lists are up to a value n, okay? And we want to add them all up, either add or subtract, right? Then it is equivalent to just separate them and do them separately, okay? And then come up with a conclusion that way. The way to prove that one is just like how we did over here. So we have an A1 plus a B1, right? Plus an A2 plus a B2, right? Plus an A3 plus a B3, plus dot, 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 plus until the very end of the list, right? AN plus BN, okay? And by properties of association, right, we can grab our A's, shove them all into one group, and grab our B's and shove them all into one group. So the very end, we'll have this, right? We can have A1 plus A2 plus A3 plus dot, 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 plus AN, right? Plus B1 plus B2 plus B3 plus dot, 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 plus BN, right? And each one of these separately is this one, and the other one is the other one, right? And the proof that I just provided here is just using the addition. The subtraction one works just as well, okay? That's the proof of that one. Next one is this one right here. So notice that suppose we had a random number C, right? So long as it's not 0, okay? And then multiplied each AI, right, by that C. And then we wanted to add them up all together. That is equivalent to just popping out the C from our summation and just doing A sub I, just summing all those up, okay? So the proof for that one is just how you would think this would go, right? So this would be on the left-hand side, this would be C times A1 plus C times A2 plus C times A3 plus dot, 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 plus C times AN, right? Since all of them have a C in common, we can factor out the C, right? So it's going to be C times A1 plus A2 plus A3 plus dot, 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 plus AN, all as a group, right? And then we can go ahead and see that all of this is just that summation. Okay? Now the last one, notice that all the A sub I are all the same, so we don't have another B sub I sequence that we're messing with here. But I want everybody to note sort of like the limits or the sort of the where we're beginning each summation and where we're ending each summation, right? Suppose that M is any value between, right, 1 to N. Okay, then we can split it up. We can split up our summation at that value M. Okay, and the way that that happens is like this. I'm going to go ahead and start with the right hand or the left hand side here, right? So the left hand side is A1 plus A2 plus A3 plus dot, 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 dot. And I'm going to keep going up to plus A M minus 1 plus A M plus A M plus 1 plus dot, 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 plus A sub N. Okay. So now what I want you guys to notice is that this right here, let me go ahead and get rid of some of the highlighting so I can go ahead and explain this very nicely. This bit right here from A1 to M is this one. Okay, notice that this summation starts at 1 and ends at M, right? And then what follows, I'm starting at M plus 1 and finishing it all the way up until N. That is this summation right here. Okay. So you can split up that M value can be anything between 1 to N, right? And you just split it right there down the middle. Okay. Okay, let's go ahead and move on. So I can go ahead and, I can go ahead and sort of keep going with this. There's so much that we're going to be doing with this over the course of the semester. I want to go ahead and introduce this a little slowly, okay? Not to overwhelm everybody, okay? Excuse me. There are a couple of equations. There are a couple of summations that do sort of reduce nicely, okay? I'm just going to start with a couple, okay? We'll pick up some more along the way. I equal 1 to N of I. If you just do this addition, so 1, 2, 3, 4, 5, 6, that reduces down to that equation right there, okay? All you really need is just that N wherever it terminates, okay? Equivalently, if you need the sum of the squared terms, so 1 squared, 2 squared, 3 squared, 4 squared, all the way up, that reduces down to this right here. All you need is the N, okay? And then lastly, let's say you want the cubes and you want to sum the cubes up to a value N, right? So 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, so on and so on. Then all you need is the N. You need where that summation terminates. That's it. Okay? So now, how do we use these? And we will sort of use them loosely here and there throughout the semester. We'll really get into this much later when we get toward the end the final third of the class, about when we do summations in series. Okay. So let's go ahead and I'm going to do an example out. Find the value of the following summation: I cubed plus 2I plus 3. Okay. All we need is these equations that are above and some of the properties that I showed you just before this, and that's all we need. Okay. So I'm going to go ahead and use the addition rule. I can split these up right? So it's going to be the sum I equal 1 to 4 I cubed plus the sum I equal 1 to 4 of 2I plus the sum I equal 1 to 4 of 3. So I'm going to break this up a little more. This one, the I cubed one, that one's fine. To 4 of I cubed. That one's already split up as much as we could do it, right? The second one, though, that one has the 2 mixed in there. So I'm going to do plus 2 times sum I equal 1 to 4 of I. So since 2 is a constant, I can just go ahead and pop it out. And that's one of our rules. Plus the sum I equal 1 to 4 of 3. Okay, now this becomes a little simpler because now they fit to the equations that are up above it. Okay, so since I'm doing the I cubed one, right, and my n is 4 in this case, so then that very first summation adds up to 4 squared, 4 plus 1 squared, all over 4, plus 2. I need the I term one, so that's the very first one. So it's going to be 4 plus 1 divided by 2 plus this one. So remember, if it's a constant value, and I'm just adding it, 4 times, that should just be 3 times 4, right? Okay. And if you go ahead and do all the math right, if you do all the arithmetic right, this one's going to be 100. The next one is going to be 20. And then the last one's going to be 12, 132. And we are done. That is our final answer right there for that one. Okay. Just to get you guys sort of in the mood, in the right mindset for how to use these. Okay. What comes up next is your very first quick check of the class. So, like I said, in the introductory video where I welcomed, me and the class itself, you are not responsible for all of them. You are only responsible for your group. So if you are in group 2, then you only need to do group 2. If you're in group 3, you only need to do the one that has that's labeled 3. Okay, that's it. Okay, as a collection, right? Another quarter of the class is doing another problem that's different from yours. I'm going to be looking at everybody's solutions once everybody's agreed onto a solution. And I'm going to grab that and post that into our notes. Okay. So you'll get all of the answers for all of these, right, eventually. Okay. And I'm hoping to get them to everybody within a week, week and a half. Okay. So go ahead, just work on the one that you're assigned. Okay. Uh, and just go ahead and make sure you post the solutions in the discussion. Okay. So I'm going to go ahead and move on. Now what I want to do is develop what we're going to use that summation for. Okay. And the reason we have that summation is for us to approximate areas. So if you guys remember from Calc 1, right, the last thing we were trying to do was we were trying to approximate the area under a curve. Okay, that's what the integral was. So I'm going to go ahead and start with the development from the beginning. Okay, and in order to do that, I need to go ahead and define what's called a partition. Okay, so a partition is a set of values xi. Okay, that start at a value a and end at a value b. Okay, such that each of those xi's, right, when you take a pair of them, consecutive pairs of them, you form small little subintervals. Okay, and that's what's called a partition. Okay, so like I said before, much of the understanding for a lot of the stuff in this class has a picture attached to it. So if you understand the picture, you understand the sort of like the concept behind it. Okay, so I'm going to go ahead and draw a interval here. Let me go ahead and insert. Come on. Shapes. There we go. I'm going to go ahead and grab this, and I'm going to go ahead and, there we go. And I'm going to make, there we go. And I'm going to start it at A, right? And end it at B, right? So then I get to divvy this up, right? And this one we know is going to be our x sub 0, and then it's going to go x1, x2, dot, 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 right? X of I minus 1, x of I, dot, 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 all the way till you get to x of n, which should be our tail, which should be our b, right? So we have these smaller subintervals, if you guys notice. There's a subinterval, there's another, there's another, there's another, there's another, okay? And the thing that I want to define now is what's called a regular partition, right? So a regular partition is when the width, the delta x, is given by b minus a divided by n. So each one of these widths, each one of these, the width of each one of these subintervals is going to be given by delta x equal b minus a divided by n. Okay, and the n is the number of partitions that we want. So if n is 17, we're going to have 17 individual smaller subintervals. Okay. Now, what are we going to use this for? We're going to use this to sort of define a left end and a right end partition approximation. Okay, so let's go ahead and continue down this way. This is probably right where, in most cases, where your Calc 1 instructor sort of ended off. Okay, so what I want to do is develop the idea behind what a right end and a left end partition is. Okay, so what I'm going to do again, I'm going to go ahead and insert a x-axis, right? And insert a y-axis. Okay, so this is going to be my y's, and this is going to be my x. I'm going to draw just a function. So this is going to be my f of x right here. Let me make it a little longer so I get enough room to, there we go. So this right here is my f of x function. Okay. So the idea here is we're trying to approximate the area under a curve, right? So, and we want to do it between a value a to a value b. Okay, so what we're going to do is we're going to start off with a regular partition of that interval a, b. So I can go ahead and sort of divvy this up just how I did before, right? So a is always going to be our x sub 0, right? It's going to be x1, x2, dot, 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 all the way till we get to the very end. This is x sub n, okay? Okay, so now, the way that this is going to work is we are going to now draw rectangles vertically, right, over each one of these subintervals. So hopefully that makes sense. I'm going to go ahead and draw the picture for you guys, okay? So I'm going to draw this rectangle up to there, okay? And that goes up to right there, right? And then I'm going to go ahead and draw the other end. Whoa, undo. I'm trying to do this without freehanding it, but I guess I'm going to have to. There we go. Okay, so that's going to be the very first rectangle. The next one goes up to right here about, and then it's going to go over and down to that one. And then it's going to go over and down to that one, right? So what I want everybody to see is that for each one of these rectangles, right, I am basing the height off of the left endpoint of each one of our intervals, okay? And what we're going to do is we're going to find the area for each one of these rectangles, okay? And remember how I said that this was a regular partition. So each one of these widths, right? Each one of these widths is delta x. Each one of these rectangles is delta x wide. Okay, so the area of this triangle, or this rectangle right here, right? The area of that rectangle right there should be delta x, because that is that length right here. This is delta x, right? Times f of x sub 0, right? So that's this one. Okay. We move on to the next one over, right? It has the same delta x with, because it's a regular partition, but now it's based off of f of x1. So the area for this rectangle is that one, right? We move on to the next one. It has the same width, delta x, and it's based off of now x2 for its height. So the area is going to be delta x times f of x2. That's going to be the area for the next rectangle over. And we do that over and over and over again, all the way till we get to the very last one. So we have an x of n minus 1. So our box here is going to be this one. Our rectangle is going to be this one right here, right? All the way up to x of n minus 1. So notice that the area for this one is this one. Okay, that is the construction for the left end approximation. Okay, and if we want to sort of write this all out in one nice big sort of expression, that is going to be this right here. Okay, this is what we call the left end approximation. The right end approximation is essentially the same thing, but instead of using the left end of each one of our subintervals, we're going to be using the right end of our subinterval. So let's go ahead and stick in an x and a y again. There we go. I'm gonna, whoa. Oh, wrong. Uh-oh. Isn't that great? Very solid, very solid. There we go. All right, let's try this again. Yeah, much better. And I'm gonna go ahead and put in another one. There we go. So we have our x, we have our y, right? And now I'm gonna make the function a little bit more pronounced. There we go. This is our f of x, right? Okay, so same thing. I'm gonna start from an a and end at b. I can divvy this up, right? Let me do it semi-equally. There we go. Okay. I can divvy this up. This is still going to be our x of 0. This is going to still be our x of n, right? The first one over is going to be x1, x2, dot, 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 right? X of I minus 1, xi, right? And I'm going to go ahead and, so like I said before, left end approximation, we're using the left end of our subintervals. Right end approximation means we need the right end of our subintervals. So the first box is going to be dictated by this height right here. So I'm going to go ahead and do that and drop this down this way. There we go. Our next height is going to be there. So over, down, and then down. And then the next one's going to be dictated by that point. So there and down. There we go. So notice how I'm working this out. The heights are dictated by the right end of our subintervals. Okay, so let's go ahead and try to sort of compile up the areas for all of these. The area for this rectangle right here is going to be f of x of 1 times delta x. Since this is still a regular partition, right, that is still delta x, right? The next one over, the area for this one, right, is going to be f of x2 times delta x. Okay, since x2 is now the right end of my subinterval, right? And so on and so forth until we get to the very end. Let me draw the one that belongs to the very end here. So I'm gonna that high, that far over, that down. There we go. So I'm basing the height off of B in this case, right? All the way until we get to B, which in our case is xn, right? And that still has the same width, right, of delta x, right? And if we want to write this all up, we want to take all those areas and add them all up. This is what we get. Okay. So the only difference between these two, right? The construction is the same for both. The only difference is in the left end, we're using the left end of our subintervals. On the right end approximations, we're using the right end of our subintervals. That's the only difference. The construction for both is still the same. Okay. So now, what I want to do now is I want to go ahead and move on and apply this really quick to an example to get us started. So if you're on a big monitor of some sort, okay, hopefully you have your phone free. If you scan the QR code, I did prep a Desmos calculator for you to use, um, just so that you don't screw up on the numbers that you're going to need to add up or calculate. Um, I'd rather you concentrate on the theory behind it, not on the computation for it. So that's why the calculator is there. Okay, so if you have your phone sort of disposable or available right there, go ahead, scan the QR code. It should redirect you to a Desmos calculator. I'm going to go ahead and show you guys what that is in a second, okay? But let me go ahead and get started with this example. So I'm going to use the left end approximations, right, to estimate the area under the curve from that function right there, 1/2 x squared plus 1, from 0 to 2 with n equal 4 partition. So I'm going to have 4 squares, okay? And I'm going to try to estimate the area under the curve from 0 to 2. So from here all the way over to here, okay? So you guys see already that um, the, the split for each one of our rectangles should be about a half, right? So let's go ahead and start there. Let's go ahead and compute our delta x, right? So our delta x, delta x is going to be b minus a divided by n, right? Our b and our a are already given. So that's my a and that's my b. It's given from the interval. So it's going to be 2 minus 0 all over 4, because we want 4 partitions, right? And that is 1/2. Okay, so we know that our splits are going to be, give me a second, there we go. Okay, we know that our splits are going to be about a half big, right? 1/2 big. So here's one split, second split, third split, and fourth split. And since we're doing left end approximations, we are doing this end. So this one's going to be this high. The next one's going to be this high. The next one's going to be this high. And the next one's going to be about this high. So here's our 4 rectangles right here. So notice that I'm using left hand approximation because that's what it's saying, right? So I'm going to try to find the area for these 4 rectangles right here. Okay. I'm going to highlight them just so that we know what we're looking at. All right, there we go. So now, this is where I'm going to be using the Desmos calculator that I gave you guys. Let me open it up really quick. All right, there we go. So the way that the Desmos calculator works is you get to give it a function, right? And you give it the x values, right? And it will go ahead and compute the function value for that function at that x value, okay? Just so that you, like I said, it's just so that you don't mess up your calculations. That would be horrible. that you sort of mess up on punching it into the calculator rather than the theory itself. So that's what's being corrected here. I want you guys to just go ahead and use this to compute the values themselves, okay? We know that our splits, thankfully it's already done, each one of our splits is supposed to be at a half, right? So we have to count them up by a half. So our very first one should be 0. The next one after that should be 0.5 because our delta is 0.5y, right? The next one after that should be 1. The one after that should be 1.5. And the one after that is going to be 2. Okay. So now I have those values computed over here on the right-hand side of the screen. Okay. And what I'm going to do now is just kind of plug stuff in. Okay. So my area, right? And I'm going to actually use the notation that I have up there. L sub 4 for this, right, is going to be 0.5 times 0, right? So it's going to be 0.5 times 1 plus 0.5 times the one at the half. So it's going to be 1.125 plus 0.5 times the one at 1, which is 1.5 plus, and now I have to scooch this over. Actually, let me just go ahead and go below it. Plus 0.5 times the one at 1.5, whoops, almost lost track of myself there, 2.125, right? So there's our 4 rectangles, right? Now, if you take a look, all of them have a 0.5. This gives you some sort of an alternate way of doing this. You can do 0.5, right, which was our delta x, of 1 plus 1.125 plus 1.5 plus 2.125. Okay. If you do all this appropriately and you add these all up, 0.5 times 5.75, and if you do the math for that, 2.875, and we are done. So the area, approximate area, underneath the curve here is about 2.875, which looks about right. I mean, it's an under approximation, right? But it's pretty close. Okay. That's it. That's the calculation for this. No more, no less. Okay. So what I want everybody to do, this is the second quick check for everybody. Okay. The odds will be doing the left-hand approximation for this function right here, negative x minus 2 quantity squared plus 4. And the evens are going to do the right-hand approximation, right? Both are going to be from 0 to 4 with n equal 8 partitions, okay? Go ahead, try these out, sort of agree on a solution for your group. And once a solution is sort of established, I'm going to copy somebody's work and I'll put that in the notes, okay? So make sure you're as clear as possible with your solutions, okay? So now moving on, moving on, I want to go ahead and now develop the idea behind a Riemann sum. Okay, a Riemann sum is exactly the same sort of development that we just did with one difference. So I'm going to go ahead and do it again. I'm going to go ahead and stick an x and a y in. Okay, here's my x and I want it in black. There we go. And then I'm going to put another one in, another y. There we go. So then these are my y's and these are my x's, right? And here's my function. Okay, and I want the same thing, an integral from A, the area under the curve, sorry, from A to B, okay? And I get to have a regular partition of A to B. So I'm gonna go ahead and divvy the x-axis up between A and B. So this is still gonna be x of 0. The next one is x of 1, x of 2, x of 3, dot, 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 right? All the way till we get to the end to x n minus 1 to b, which is x sub n, right? And they divide into subintervals, right? So each one of these, this is going to be an x I minus 1 to an xi. Those are going to be my subintervals. Okay. The idea behind a Riemann sum is the choice of our height for our rectangles. Okay. And in left-hand approximation and in right-hand approximation, we just chose the left endpoint or the right endpoint. In actuality, we can choose any point between the left and the right endpoints for our subinterval. It doesn't matter which point to choose. Okay, so what does that mean? I'm purposely doing this. I'm picking a rando point that's not the middle. Okay, and this is going to be our x of I star. Okay, that value is what's going to dictate our height. So I'm going to go ahead and sort of carry this up to right here, right? And then this is going to be the left bar, and this is going to be the right bar, right up to there about. There we go. That is the only difference. It is dictated by sort of a rando xi star point, right? That's somewhere inside our subinterval, okay? Whenever we do that, we have what's called a Riemann sum, okay? And the Riemann sum, it's the same construction as before, right? It's all of these areas, the area of each one of these boxes, right? And just added them all up. That's it, okay? So now, why do we have Riemann sums? Like I said, we're trying to approximate the area under the curve, right? And at the moment, we only have what we've been doing just now is we've been dividing them up into smaller subintervals. So we did 4, we've done 8. In the lecture questions, you're going to do 16, right? But the idea is we want to get those, if we want an accurate, the most accurate approximation to the area under a curve, we want those partitions, right? We want those subintervals to be infinitely small, very, very tiny, okay? And how do we do that? We need to take a limit, okay? So that's how we end up doing our integrals. So then we take the divisions of our interval AB and make them infinitely large, which makes each one of our partitions infinitely small, okay? And the smaller and smaller we get it, the closer and closer we get to the actual area under the curve, okay? And that's how we define our integral. So this is going to be the last definition I'm going to do for the course for this section. Suppose that f of x is continuous and non-negative. We're going to get rid of this word eventually, okay? Over an interval AB, okay? And let this be the Riemann sum, okay? And this is forgetting something, actually. It's supposed to have an xi star, okay? And then the area of under the curve, right, is given by this equation right here, right? The limit as n goes to infinity. So I'm making my, I'm dividing up I'm dividing up my interval into smaller subintervals, right? And each one of those smaller subintervals is infinitely much more skinnier, okay? This is what's going to be our definition for the integral from a to b of f of x dx. Okay. And I believe that is it for this section. Yes, that is. Lecture questions come up after this. So go ahead, access the notes. Make sure you fill out, make sure you complete all the lecture questions. This one has 2 pages worth. So make sure you complete all of those. Okay. If you have any questions, make sure to check my my weekly semester schedule to see where you can find me. I have some time in the math tutoring center, and I do have the all day online for particularly this class. Okay. Besides that, I'm all done. Happy studying.